The moon is a place of deadly extremes. In the depths of the craters near its poles, sunlight has never touched the ground, not once in billions of years. These eternal shadows hide ice, pitch-black vacuum, and cold so intense that it rivals the most distant corners of the solar system. Yet this harsh realm has become the prize of a new space race. Major powers, particularly the United States and China, are quietly competing to reach the darkest places on the moon. So what priceless secret could be hidden within this darkness? What might be lurking in the moon's most dangerous place? In the next few minutes, we'll lift the veil of mystery over the moon's permanently shadowed regions and find out where the electrostatic traps with hundreds of thousands of volts come from. What kind of overwhelming toxic threat is hidden in the local dust? And why China and the United States are planning to send astronauts there, despite all the risks. Who, in the end, might gain the right to own these regions and exploit their resources? Let's find out. From a distance, the moon looks calm. No weather, no oceans, no air. A world that should behave like a perfectly sealed vacuum chamber. And yet the South Pole introduces a contradiction into this story. Water appears where it shouldn't exist, not as rivers or frost-covered plains, but as signals and instruments, as molecules that appear and vanish, and as ice locked away in places that sunlight has never reached. The problem is this: if sunlight and vacuum should be removing water, then either something is constantly creating it, or something is holding on to it with astonishing efficiency. And both answers point to the same place: the polar shadows. These permanently shadowed regions aren't just cold areas. They're natural cold traps, places that can stay below water sublimation point for geological timescales. If there's ice there in significant quantities, it changes the economics of all future missions. Water for life support, oxygen for breathing, and hydrogen and oxygen for fuel. But the very same place that could sustain a base can also destroy it. At the poles, technology faces conditions unseen in the Apollo footage. Extreme cold that can seize up machinery, darkness that strips away the benefits of cheap solar power, and a dusty environment that behaves like electrically charged glass powder. Here, the story becomes even more tense. The moon's most valuable resource lies in its most hostile terrain, and the map of where ice might be overlaps with the map of where missions want to land. It's precisely because of this overlap that the South Pole is no longer just a scientific target. It's become strategic. Timing, landing sites, and partnerships suddenly matter, because the first infrastructure placed near these craters will determine which opportunities become available to everyone else. But before anyone argues over who will get there first, our evidence needs to stop being just maybe. Because for decades, every hint of water on the moon had an explanation: contamination, instrument noise, or a signal that could mean something else. So when did this story cross the line from suspicion to evidence? For most of history, the moon was thought to be completely dry. The first signs that this assumption might be wrong appeared in 1976, when the Soviet Luna 24 probe drilled into the lunar soil and returned samples to Earth. To scientists' surprise, the regolith contained about 0.1% water by mass, with even more water found in the deeper layers. At the time, this result was largely dismissed as likely contamination from Earth. After all, how could water survive on an airless moon? In 1994, a breakthrough mission changed the picture. NASA's orbital spacecraft Clementine mapped the moon and discovered that some craters near the poles are in permanent shadow, never seeing sunlight due to the moon's slight axial tilt. These regions, some of which hadn't seen sunlight for billions of years, immediately captured scientists' attention. If comets or meteoroids containing water had struck the moon, ice might still be hiding at the pitch-black bottoms of these craters, preserved at temperatures around -280 degrees Fahrenheit or lower. Clementine's discovery sparked intense debate and plans to explore these permanently shadowed regions, or PSRs. In pursuit of further exploration, NASA launched Lunar Prospector in 1998. This small orbital spacecraft was equipped with a neuron spectrometer to detect hydrogen, a key indicator of water. As expected, Prospector found significantly enhanced hydrogen signals at both poles. The data suggested that polar craters could contain between 10 and 300 million tons of water ice. It was an enticing figure, but hydrogen alone was not conclusive evidence. It could indicate the presence of hydroxyl, OH, or other hydrogen compounds rather than H2O. To find definitive proof, mission leaders took a bold step at the end of Prospector's mission. In 1999, they deliberately crashed the spacecraft into a southern polar crater, hoping to eject ice that telescopes on Earth could detect. However, no signs of water were observed after the impact, leaving the mystery unresolved. Other space agencies joined the search. Japan's Kagaya orbiter, launched in 2007, created high-resolution maps of the moon, including its dark craters. Kagaya also ended its mission with a controlled impact near the South Pole, and once again, no obvious traces of water ice were found in the ejected material. By the late 2000s, evidence was accumulating, but still remained indirect. The situation changed dramatically with India's Chandrayaan-1 mission in 2008. Chandrayaan deployed the Moon Impact Probe, which plummeted toward Shackleton Crater at the South Pole. During its 25-minute descent, the onboard mass spectrometer sampled the extremely thin lunar exosphere and finally confirmed the presence of water molecules nearby. The orbiter itself carried NASA's Moon Mineralogy Mapper, which shortly afterward detected water and hydroxyl on the lunar surface from orbit for the first time. This was a double triumph. Water was discovered both in the polar darkness and, unexpectedly, in trace amounts even in the sunlit lunar soil. By this point, NASA was confident enough to organize a mission for direct confirmation. In 2009, NASA launched LCROSS, the Lunar Crater Observation and Sensing Satellite, alongside the Lunar Reconnaissance Orbiter. LCROSS took a dramatic approach. It kept the empty upper stage of its rocket and then directed this 2.3-ton booster to collide with the shadowed Cabeus crater near the South Pole. The spacecraft followed the impact closely, flying through the plume of debris and vaporized material. This time, the results were unambiguous. As the sunlit plume rose above the crater's rim, LCROSS instruments detected a variety of volatiles: water vapor, hydrogen, ammonia, methane, carbon monoxide, and carbon dioxide, all ejected from the previously hidden soil. Most importantly, the signs of water ice were undeniable. The hydrogen detected by the Lunar Prospector was indeed locked in frozen water. The soil of the shadowed crater was found to be rich in water ice and other useful compounds, making it a true treasure trove of resources. This chart shows confirmed ice deposits on the Moon's south pole on the left and north pole on the right. The blue area indicates detected ice. As expected, the ice accumulations are located in the coldest, darkest spots inside polar craters that never see sunlight. This was the first undeniable evidence of water ice on the lunar surface. Scientists estimate that these regions could contain a staggering amount of ice, around 600 million tons. In other words, roughly half the volume of Lake Travis in Texas. Almost all of it is locked away inside those cold, dark craters, yet the Moon isn't completely dry outside the shadows. LRO and other instruments have detected traces of water migrating across the sunlit lunar surface. By lunar noon, surface moisture evaporates, but it reappears during the cold lunar night. In 2020, NASA's SOFIA Airborne Telescope even detected H2O molecules in sunlit soil near Clavius Crater. Though in extremely low concentrations, about 200 parts per million, roughly 100 times drier than the Sahara Desert on Earth. These discoveries suggest that the Moon has a modest transient water cycle and multiple sources of water. Ancient comet impacts, asteroid delivery, solar wind chemistry, and constant micrometeorite bombardment all contribute to its local water budget. Still, most of the Moon's water is ancient ice hidden in permanent shadow. Scientists believe that over billions of years, water delivered by comets or produced by solar wind reactions migrated toward the poles and became trapped in these natural deep freeze vaults. Once a water molecule falls into a pitch-black crater, it never warms enough to escape and becomes part of a growing reservoir of ice buried beneath dust. These locations are essentially time capsules, preserving water and other volatile ices that may date back to the early history of the solar system. For planetary scientists, this is incredibly exciting. These ices hold clues to the Moon's past and to how water was delivered throughout the solar system. For engineers and explorers, it's even more thrilling. Water is often called space oil, a resource so vital that its availability could enable humanity to explore the solar system more effectively. With water on the Moon, astronauts could potentially produce drinking water, breathable oxygen, and even rocket fuel by splitting water into hydrogen and oxygen. Otherwise, all of it would have to be launched from Earth at an enormous cost. These reserves could become the stepping stone that turns the Moon into a fuel depot and base camp for deeper space missions. In short, whoever can extract the polar ice will gain a decisive advantage in exploring and commercializing the solar system. But more on that later. Before that can happen, we have to solve a difficult problem: gaining access to the most hostile environment on the Moon and surviving it. What makes the Moon's permanently shadowed regions so extreme? First and foremost, complete darkness. The floors of these craters haven't seen sunlight for millions of years because the Moon's axial tilt is only about 1.5 degrees, meaning the sun never rises high above the horizon at the poles. Tall crater rims and mountains cast eternal shadows. Inside, a lunar explorer must rely entirely on lamps or sensors, much like exploring a cave. This creates obvious practical challenges. Solar-powered equipment doesn't work without direct sunlight, and navigation or construction in the dark becomes extremely difficult. Hand in hand with the darkness comes incredible cold. The floor of polar craters are some of the coldest places in the entire solar system. Data from the Diviner Thermal Instrument on LRO showed that in some locations, temperatures dropped to 25 Kelvin, which is around negative 415 degrees Fahrenheit. That's colder than Pluto's average temperature, and only a few degrees above absolute zero. For comparison, temperatures at the Moon's equator range from about plus 250 degrees Fahrenheit during the day to minus 200 degrees Fahrenheit at night. These findings stunned scientists. They simply didn't expect it could get this cold. At such temperatures, the soil becomes hard as rock and instantly freezes any spacecraft fuel or unprotected electronics. Materials become brittle, lubricants and battery fluids solidify. Operating rovers or drills in these conditions require special engineering solutions, such as nuclear heaters or continuous power to prevent freezing. Even surviving a typical lunar night, which lasts about 14 Earth days, in hibernation mode is challenging. Here, however, the night is permanent. For this reason, any future lunar base would likely avoid the deep interiors of PSRs. Instead, plans often call for placement on nearby sunlit ridges or peaks of eternal light. These are mountain peaks and crater rims that receive nearly constant sunlight, only dipping into shadow briefly each month. Temperatures at these peaks hover around a relatively manageable negative 60 degrees Fahrenheit. These locations are ideal. They lie close to ice-rich craters while still being sunlit, allowing for the use of solar power. One well-known example is the rim of Shackleton Crater. Here we see the stark contrast of light and darkness at the Moon's south pole. The sunlit rims of Shackleton Crater are visible, while the center yawns into pitch-black emptiness. This mosaic was created by NASA's new Shadow Cam, an instrument capable of capturing details under extremely low light. It provides a rare opportunity to see what the human eye cannot: the crater floor, frozen for millions of years. The uneven terrain inside is illuminated only by faint reflections and starlight, yet ShadowCam was able to reveal slopes, boulders, and possibly frost-covered areas. The physical environment in these craters is not only cold and dark, but likely mysterious in other ways. Without sunlight, there are no regular daily temperature cycles or the electrical charging effects of the lunar day. Scientists suggest that the local soil regolith in PSRs may have unique properties. It could be fluffier or more porous, as indicated by the L-cross impact, which produced a dimmer plume than expected. Eternal cold may cement ice grains together, or conversely, micrometeorite impacts may grind the top layer into unusually fine powder. Instruments such as the Lyman Alpha Mapping Project on LRO have peered into some shadows and detected signs of surface frost or ice crystals mixed with soil. Beyond water, these cold traps likely contain a whole pantry of volatiles, small amounts of everything from carbon dioxide to ammonia and methane. From a geological perspective, PSRs are a scientific gold mine. Yet all these riches lie behind a formidable environmental barrier that goes beyond the cold. Another quirk of the lunar poles involves electrostatics and dust, which we'll examine in more detail later. Even in darkness, the Moon's surface accumulates electric charge. Ultraviolet sunlight and solar wind plasma knock electrons from the soil on the sunlit side, giving dust grains a positive charge. In shadow, grains can become negatively charged. At the terminator, the boundary between light and dark, electric fields can actually levitate fine dust grains above the surface. On the lunar day side, Apollo astronauts observed a curious horizon glow at twilight, which they interpreted as sunlight scattered by levitating dust. On the night side, or within PSRs, the electrostatic environment can cause dust to drift and settle in new locations. These effects may drive fine dust into shadowed regions, forming thick powder deposits at the bottoms of some craters. In essence, the moon's charged dust can slowly flow from light areas into the dark, becoming trapped there much like water molecules. And now a few historical facts. 12 people walked on the moon during the Apollo missions, and all 12 reported some form of respiratory or eye irritation from the local dust. This was the first indication that lunar dust was not just a nuisance, it posed a real health hazard. What makes lunar dust so dangerous? The answer lies partly in its physical properties. Lunar dust grains are microscopic, jagged, and relentless. Unlike Earth dust, which is often smoothed by wind or water erosion, lunar dust is as fine as powder yet sharp as broken glass. Each particle is the result of billions of years of meteoroid impacts grinding rock into powder. Without an atmosphere or water to dull the edges, the grains remain razor sharp. When astronauts walked on the moon, this abrasive dust clung to their spacesuits, boots, and tools due to static charge, while also mechanically embedding itself into surfaces. Low lunar gravity means that once dust is kicked up, it falls slowly and lingers longer in the air, reaching every nook and cranny. Apollo crews found that after returning from the surface, dust had infiltrated their spacecraft, coating control panels and even their lungs. Mechanically, the dust is extremely abrasive. These tiny, sharp grains wore down Kevlar-like layers on spacesuit boots and damaged vacuum seals on sample containers. It was like fine sandpaper, grinding every accessible surface. Operating equipment under these conditions for weeks or months poses a serious challenge. Dust can scratch visors, jam hinges, clog bearings, and coat radiators and solar panels, reducing efficiency. NASA called lunar dust the #1 enemy for future explorers. And because it's electrostatically charged, it's very hard to remove, sticking to surfaces and even levitating in the vacuum. From a health perspective, long-term inhalation is a major concern. Lunar dust particles vary in size, but a significant portion is extremely fine, on the order of tens of microns or smaller. Particles 50 times thinner than a human hair can penetrate deep into the lungs and remain there for months. The longer they stay, the higher the risk of toxic effects or tissue damage. On Earth, inhaling silicate dust found in mines or volcanic ash can harm the lungs and cause disease. Lunar dust is also rich in silicates and oxides, with the added hazard of sharp edges and chemically reactive surfaces due to constant solar and cosmic radiation. Laboratory studies have shown that simulated lunar dust can kill cells and damage DNA. One research team mixed various lunar soil stimulants with human lung cells and mouse brain cells in petri dishes. All samples caused some degree of cell death or DNA damage, with the finest dust particles killing up to 90% of cells within just 24 hours. Such DNA damage could, over time, lead to cancer or neurodegenerative diseases. In another study, rats were exposed to inhaled lunar dust, which caused lung inflammation and toxicity that worsened with increased doses over 13 weeks. Most alarming in rodent experiments, the finest submicron dust particles were even able to travel from the nasal passages into the brain via the olfactory nerves. While we don't yet know if the same would happen in humans, this highlights that exposure to lunar dust is not something to take lightly. NASA scientists such as Dr. Kim Prisk note, this may prove to be the largest routine challenge to the lung in future space exploration, as we know we can't set an exposure standard of 0. The Apollo astronauts' hay fever was likely just an acute irritation. The real danger for people living on the moon could lie in long-term lung damage, weakened immune systems, or other diseases. Even more concerning is the fact that even with careful cleaning and safety procedures, electrostatically charged particles still cling to spacesuits and tools, later becoming a problem inside habitats. That's why today scientists are developing modern designs focused on preventing dust intrusion rather than cleaning it afterward. Stricter airlock protocols, suit isolation concepts, and active surface cleaning systems such as an electrodynamic dust shields, which use electric fields to remove particles from critical surfaces. In a recent experiment conducted during Firefly Aerospace's Blue Ghost Mission 1 in 2025, such a system successfully cleared dust from a camera lens and a radiator on the Moon. Dust is something most people don't think about. It's not glamorous, but it determines whether a base will keep running on day 30 or fail by day 300. And once dust is brought under control, the question won't be whether anyone can survive there. It will become, who can build a working system here first? With this in mind, the world's leading space agencies are quietly but intensely competing for the right to be the first to extract polar ice. The United States has clearly focused NASA's Artemis lunar return program on the South Pole. Artemis aims to land astronauts on the Moon for the first time since Apollo, specifically in an area rich in polar ice. According to current plans, Artemis 3 will attempt a south polar landing by mid-2027 or at the latest 2028. NASA has identified several potential landing zones near Shackleton Crater. By 2028-2030, the agency and its partners plan to establish a small Artemis base at the South Pole. The base will likely be located on a high ridge with a near constant sunlight for power adjacent to a PSR with accessible ice. Originally, the Viper rover was intended to scout the Moon's South Pole ahead of crewed missions, but in 2024, NASA canceled the project due to budget cuts. If the Artemis program succeeds, by the early 2030s, the U.S. and its partners could have an outpost where astronauts regularly extract ice, test oxygen production, and demonstrate technologies needed to live off the land on the Moon. Meanwhile, China has emerged as another serious contender for the South Pole of our satellite. Their long-term vision remains the ambitious International Lunar Research Station, ILRS, in the 2030s, which China presents as an open program with external partners. According to Reuters, as of 2025, ILRS has 17 partners, far fewer than the Artemis Accords coalition, but the number of collaborators continues to grow. The first steps of this plan will be robotic. Chang'e 6, Chang'e 7, and Chang'e 8, three Chinese missions scheduled for 2024 to 2028, are all targeting the South Polar region. Chang'e 6 has already been completed. It was launched in May 2024 and returned to Earth June 25, 2024, bringing back the first ever samples from the Moon's far side, the South Pole Aitken Basin. Chang'e 7 is publicly described as a 2026 mission, likely including a lander, rover, and mini flying probe to search for water ice and study the environment in permanently shadowed regions. Chang'e 8 is planned for launch in 2029, aiming to test in situ resource utilization technologies such as 3D printing structures from regolith and potentially begin constructing base infrastructure. By 2030, China intends to establish the first robotic station at the Moon's South Pole, with discussions of a permanent crewed research base in the mid-2030s. Meanwhile, Russia's lunar program, China's declared partner in the ILRS, suffered a public setback with the Luna 25 crash in 2023, and its role now appears diminished. Nevertheless, the Russia-China ILRS framework remains on paper. It's worth noting that India, having just succeeded with Chandrayaan-3, is also eyeing the polar prize. The Chandrayaan-3 rover briefly operated in sunlight north of a PSR, and India has expressed interest in future missions for direct ice extraction. Japan, the European Space Agency, and other participants also have various plans for exploring the lunar poles, often in cooperation with Artemis or ILRS programs. Even private companies like Intuitive Machines, Firefly, Blue Origin, Astrobotic, Lunar Outpost, and others see opportunities. They're developing small landers and rovers for reconnaissance, and commercial ventures are being discussed to mine lunar ice for sale, for instance, as fuel supply for satellites or spacecraft headed to Mars. In many ways, the race to the lunar poles resembles the Cold War-era space race, but with 21st century characteristics. It's not just about planting a flag, it's about securing resources and strategic footholds. The country or coalition that first masters lunar water extraction will gain not only prestige, but real economic and operational advantages in space. Rocket fuel produced on the moon could dramatically reduce the cost of deep space missions, since refueling in low gravity is far cheaper than transporting all fuel from Earth. Every ton of water ice converted into rocket fuel can save several tons of launch mass from Earth, opening the door to more ambitious missions such as crewed flights to Mars or the construction of large orbital infrastructure. Beyond fuel, local water provides life support for lunar inhabitants, removing one of the major obstacles to long-term stays. It's easy to see why the U.S. and China, in particular, view the South Pole as a strategically critical high ground. NASA Administrator Bill Nelson even warned that the U.S. must watch out that China doesn't get to the place and say, "This is ours now and you stay out," expressing concern that China could attempt to dominate the area's richest in ice. China, of course, denies any intent to exclude others, stating that its interest is purely scientific and aimed at benefiting everyone. Nevertheless, both countries are moving quickly, and timing matters not just for prestige, but for position. At the South Pole, there are only a few suitable corridors that balance sunlight, safe terrain, and accessible ice. Once the first real infrastructure is established, everyone else is forced to build around it. Thus, the pressure becomes simple yet subtle. Fall behind, and the best ground is already taken, without anyone ever having to say the word claimed.